Hi everyone. So welcome to today's MICCAI Industrial Talk. I'm Dakai Jin from Medical AI Lab at Alibaba Damo Academy. So today we are really excited and glad to invite two speakers from Nvidia to talk about the open source foundation models for 3D medical image segmentation and generation. So our first talk is, the title is Vista 3D, a unified segmentation foundation model for 3D medical imaging. Our speaker is Dr. Yufan He. So Yufan is an applied research scientist at Nvidia. His research interests include medical image segmentation, AutoML, and foundation models. He obtained his PhD from Johns Hopkins University and is a recipient of the MICCAI Young Scientist Award on 2019. So I'll give the time to Yufan. Yufan, you can share your screen.
Yep, thanks, Takai. Yeah.
Yeah.
Let me start. Yep, thanks everyone for joining. Today, I'm going to talk about a topic called the Vista 3D, the versatile imaging segmentation and annotation model. And also thanks to other main contributors, the Pengfei, Yuchen, Daguan, and Wenqi for their contribution to this project. And first we will talk about the motivation and the NIM demo, the NVIDIA NIM demo, and the model performance, and last about the method details. So for 3D segmentation models, the past few years is always about the task-specific models for automatic segmentation, like the NUNet, Auto3D-Seg, or architectures like convolution, transformers, or hybrid models. People are developing those specific models of frameworks to segment a certain task. And recently, people are starting to develop those large models to segment a lot of things, like the total segmentator or continuous seg. Those models can segment the hundreds classes with the same one, so people can use them out of the box. But the problem with those models is that they can only segment the scene classes during training. But foundation models from the large language models, they have shown strong generalizabilities on various tasks. So people are starting to develop the real foundation models that's trying to perform the segmentation on unseen structures based on user-provided prompts. And there are three ways. The most ideal way is doing the open vocabulary segmentation. You combine text with the image segmentation. People can use task descriptions to segment this. But unfortunately, this is an unsolved problem, and some work are exploring this, but they are not able to perform open vocabulary segmentation. The other direction is using example-based. It's easier. You provide image label pairs for those unseen classes, and there are preliminary results, but still the performance is lacking behind those leading 3D segmentation models. And the last is the interactive using clicks, boxes, or masks. And this is easier. So Meta is segment anything and segment anything in videos. After training on a huge amount of natural images, and they show this impressive zero-shot ability. But they have internal problems because they are built on 2D networks. And when you use 2D networks to solve 3D problems, usually you will see like 5 to 10% the lower performance compared to those leading 3D expert models. And also the other problem is the interactive segmentation, especially in 2D, is still too much effort. People want to do automatic segmentation. And when you annotate slice by slice, it's really slow. Also, it's not suitable for those large cohort analysis. So Vista 3D, the motivation is we want to build an easy-to-use workflow that cover most advancements in foundation models and can really save the annotation effort. And our solution is we build a unified model that supports accurate automatic segmentation for most classes and 3D interactive annotation with zero-shot ability. And this figure shows the general overflow, the workflow that Vista 3 is trying to support. So user only need to provide an image, also the class X that they're trying to segment. And if this class X belongs to a supported class, we have a 127 supported class list, including most common organs. like liver, pancreas, all this can always be expanded. So people won't want to do interactive segmentation for common classes like liver, pancreas. They're already solved problems, right? So if you give X, if this X belongs to those common organs, Vista 3D directly do automatic segmentation. And this takes no human effort. And then we got the automatic segmentation. The doctors can take a look at it. If it's good, then directly use it. If it's not good, and the annotators, the doctors can click several 3D click points to fix those error regions, and it goes into this loop. So by using this, for most common organs, you save 99% of the annotator's time. So if this X is some novel tumor or some from animal data, then none of those automatic models can segment. We require this. We use a SAM-like thing. We require the annotators to provide some 3D click points to do interactive segmentation. So since the segmentation is performed in 3D, so it's also very efficient. So this is the workflow that Vista 3D trying to support. And the key point is for Vista 3D is this is the best unified model that supports a full annotation workflow. And it supports the automatic 3D CT segmentation. It supports 127 classes, including 7 types of tumors lesions. And it's trained on over 11,000 CT scans on 25 public data sets to show, and has a strong generalizability. Also, it supports the 3D interactive segmentation. It supports the efficient interactive segmentation in 3D. A user can use clicks to segment those supported class or refine those automatic segmentation. And it has the strong zero-shot abilities. And also, the performance-wise, to achieve the state-of-the-art accuracy, you compare it with Auto3DSeg, NUNet, and TOE segmentator on diverse benchmarks. And we also compare it to other foundation models like MATSAM and SegVol. Last, it's the whole project is open source. All the model weights, training, evaluation, data curation are open source. Also, the model has been integrated into MAISI 1.4 and the Model Zoo, so it's very easy to deploy. We also provide the Nvidia NIM service demo and OHIP plugins for interactive segmentation. The paper code and demo can be found in this link. Here we show the Nvidia NIM 3D demo. So here is this is the online demo. You can click the segment everything, so it will automatically generate the segmentations. Also, this is also promptable. You can select for example, the liver you want to segment, and it's going to perform automatic segmentation. And you can take a look to see what is you're not satisfied. For example, this part, we're not satisfied, then we just click on 2 points, and then the model will click correct those results. This saves a lot of manual annotation effort. Yeah, so if it's a class that's never seen, for example, some random thing here, and you just generate a new class and you click a point and click run. And you get the zero-shot segmentation on 3D space. So this is the online name demo. And I think our engineer team are building a local version of the name. Also, we will have the OHIF plugins. So this is the results. We first do the automatic segmentation results on this 127 supported class. We compare with those state-of-the-art supervised training pipelines like the NUNet and Auto3DSeg. So we train the NUNet and Auto3DSeg on every individual task and report the task set results. Also, we compare with the TOE segmentator. We directly apply this out of box and segment all those classes. We also tested on SAM and SAM2. We fine-tuned this, but we found these 2D methods are still lagging behind those top 3D models. So if you look at tables, we benchmark on all those diverse data set, and these are the Auto3DSeg NUNet and TOE segmentator results. And this is the Vista 3D Auto, directly using this for automatic segmentation. This column is the Vista 3D point. We click one point for each organ. And this is the dice results. And this is the auto plus point, means we have the automatic results and we click a point either on false positive, false negative to correct the region. And we see when directly applying Vista 3D out of box is achieving comparable results with all those expert models. When you have a minimum human input, it's going to give you much better, even better results. There is one thing we need to take a look at the total emitter V2 results. Vista 3D already achieved the very high results, but total emitter is 94 because this data set is built on top of the total emitter. Also, it's built on top of MINUNet. So it's a kind of bias to this, but this 89 is also a very high number. So another is the inference speed. We compared it with those emitter on the 16 gigabytes GPU. This is the size of the volume, and this is the running time. Since this is doing the automatic segmentation for 170 class for Vista 3D, 118 for Vista 3D, and 117 for the total emitter. So they're comparable. We see this Vista 3D is much faster because total emitter is using 5 models to segment all those classes, but Vista 3D is 1 model to segment the over 117 classes. And the GPU requirements it depends on user prompt and the image size, because this is purely promptable. User can provide any number of prompts, and when you provide more prompts, it takes larger GPU memory. And the model can be trained on 16G GPU by adjusting the prompt number, and can be inferenced on 12G GPUs on regular size CT or smaller based on your user prompts. So you can always trade off between the time and the GPU memory. This is qualitative results. We performed the out-of-box automatic segmentation on NIH monkey data. This is has a big domain gap as human body, and we show this the Vista 3D is much more robust on this animal data. This is other comparisons with the recent SAM-based interactive models like the SegVol and MedSam. This is for the automatic segmentation on the pancreas, so it's semantic. MedSam is using a bounding box and only on 2D, so Vista 3D can achieve a pretty complete segmentation. This is for the hepatic vessel. This is for the interactive. We click a point here. This SegVol also click a point here. This is the 3D visualization of the hepatic vessel. And I think Vista 3D achieves much better results in the details. For bounding box, the problem is you cannot do any fine detailed segmentation. Like you cannot determine if it's a liver or it's a vessel. Here we show the zero-shot interactive results. So here we found a mouse CT dataset. This mouse dataset looks like this. This is a high-resolution micro CT, and none of those existing models that can do automatic segmentation on this. So we are relying on zero-shot. And here we compare with several baselines. So the axis, if you look at this figure, this is for the left lung, and the x-axis is the annotation effort. So it means the click points, how many click points you're using. And for bounding boxes, each bounding box is considered as 2 points. The y-axis is the die scores. So we see this green line is the Vista 3D. So if you click a few points, you can easily reach a very high results. And because this is in 3D, so it's more efficient. This is MedSam. Because MedSam takes a lot of more points because it has to annotate slice by slice. The SegVol, I use their default setting. They're using 7 points here. The dashed line is a variant of Vista 3D that we did as an ablation study. We don't use the super voxel for training. So we see the result is still not good for this dashed line. This is for the heart. We see this is the results. And this is for the right lung, and this is for the spinal cord. We see that the 3D achieved a much efficient annotation for zero shot and with a much less annotation effort. This is some other examples for three tumors. It's the same. This is the Vista 3D. This is the Vista 3D without the supervoxel training. And this is SACVO, and this is the MESAM. And this is the crossing point. The last step, because the purpose of annotation is always about training an automatic model for large cohort analysis. So we did some fine-tuning results to show if this pre-trained checkpoint is better for transfer learning. And for this mouse CT dataset, we iterate the number of training cases from 1 to 89. 89 is the full dataset. And we trained all of the NUNet from scratch and the total imitator pre-trained checkpoint and fine-tune it using NUNet pipeline. And you see the with 5, they can be pretty high, but Vista 3D is best. So the gain is it's more clear when in the few shot settings. But when with the full data set, still achieves comparable results with host imitator. And for Word data set, we did the same thing. There are several classes in Word that is not supported in the Vista 3D, so we tested on this one. So when you have a few annotated examples, those models, NUNet L3sec, they cannot be trained well with a few annotated examples. But the Vista 3D or those annotator, they're able to boost up the training of this on new data sets. And so here we introduced the method details. So to train this model, we have several novelties from the model architecture design, dataset curation, and the training recipe. For model architecture, we have a dual branch design with 3D SAM hats and well-established 3D components. The dataset curation, we curate a large diverse dataset and paired it with pseudo-label and the super voxels. And the training recipe, we have a 4-stage training recipe to solve the data imbalance issue and the 2-branch conflicts during training, also lots of the performance issues. So for the model architecture, we have this dual branch design, and this is we use a patch-based and sliding window inference, simply because if you look at the recent MICCAI challenges or the top performing models is always mostly based on the patch and the sliding window with 3D backbones. And we just use this. This is the SecResNet 3D encoder and decoder, and with a 3D patch input and the sliding window. And we use this encoder decoder to extract the features, and then the top branch is performing the automatic segmentation. And here we use a class prompt, which is classic. We curate a class list of 127 classes. And also we have this embedding. So for each class, we have an embedding. And we use this embedding to perform a linear projection to segment to get the automatic results. And notice we use sigmoid instead of a softmax because we are doing the binary segmentation based on the input prompt. There are several works that's trying to use clip embedding or other pre-trained embedding from text. We found this, if you use clip embedding, it's actually giving you worse results because they are frozen or the text information is not really helpful here. And here we just use some random embedding, and they use the sigmoid to perform the binary segmentation. This is for the automatic branch. The bottom branch is the interactive branch. Here we use the decoder to upsample it to a very high resolution to keep all the details. If you look at a SAM or SAM2, they don't have this. And we use the point prompt. This is the X, Y, Y, Z, I. This is from the 3D space, and also with the point labels. Here we use the same prompt head as the segment anything, but we change it all to 3D. And it performs some cross-attention between the feature maps and the point prompt and get the interactive results. This is also interactive segmentation, in binary segmentation. And the last, if user provide the class prompt and some point clicks, it means people trying to correct the automatic results. So we have a post-processing merge algorithm that takes the point, clicks, and the interactive results to fix those automatic results. This is based on very sophisticated post-processing to achieve this editing behavior of the Vista 3D. For dataset curation, we curated over 11,000 CT scans with partial labels, pseudo labels, and super voxels. For partial labels, it's actually the manual ground truths from each dataset. And we mapped it to a global index because the definition of liver in different dataset could be different. The class index, they're different. So we mapped it to a global index. For pseudo labels, we generate the segmentation for every scan using the dosimeter model. This is used to improve the robustness because the huge class difference, for example, the lung tumor, only have a few scans, and the model can easily remember that the lung tumor only comes from this data set. Without pseudo labels, the model will easily overfit to certain data sets. The last is the super voxels. The super voxel is crucial for giving this model zero-shot ability. So we found that if you only train a model on a few hundred classes of medical data, the diversity of the class labels are not able to give your model a strong generalizability. So the only way we found is to distill the information from those large natural images, either using their pre-trained checkpoint. I think most work is trying to fine-tune the SAM2 pre-trained checkpoint. SAM or SAM2 is pre-trained checkpoint because they can reuse the information, the zero-shot ability from those pre-trained checkpoint. But if we want the 3D networks, we have to find a way to convert those 2D checkpoints or the 2D data sets into a 3D and make the 3D network learn. Here we use a method called the 3D super voxels. We generate the feature maps using SAM on 3 views and combine them together, and then use a 3D slick algorithm. This is the generated super voxel, and this gives improve the Vista 3D zero shot by over 50%, since we train on a data set like this. And this is the data set we curated. And the training recipe, we have 4 stages training. Is trying to solve the 2 branch conflicts, data imbalance, and performance issues. We first trained this point branch with supervoxel. We first trained this branch with supervoxel, pseudo labels, and partial labels. Those labels are noisy and they're may not trustworthy. And but the intuition is just trying to train a strong encoder, and we use iterative sampling and all the techniques to make sure that the model is following the click points. When you train a model like this on medical data, it's very easily to overfit to a certain organ. For example, because the liver, spleen, they're pretty stable across data sets, and it's very easily that the model directly ignore your point clicks, and they know what liver looks like, they know what the spleen look like, and they will ignore the point clicks. So we use the different methods to avoid this and make sure the model is listening to your click points and can be refined using click points, the results. So this is first step. We train this point branch first, and the other problem is the data imbalance issue. So we have lots of liver segmentations, but we have a very few liver tumors. And if you train them all together in the first stage, the liver tumor will soon overfit. And so in this way, in the first stage, we didn't oversample the liver tumors, and we left all those underrepresented class into the second stage. So we fine-tune this point branch with underrepresented data sets to solve this data imbalance issue. So after training this interactive branch, we freeze the encoder and started training the auto branch, this upper branch, using the regular supervised training. And after training this, the third stage, we still repeat the second stage, like we fine-tune this branch to improve the performance of those underrepresented classes. Besides oversampling, we generate a lot of synthetic data from MAISI that Han will introduce in the later presentation. And that this is all this training is trying to improve the results and solve all those challenges. So the summary is Visa 3D supports a workflow with state-of-art automatic interactive editing at zero shot and the fine-tuning ability. Also, it's fully open source, easy to use with OHIP plugins, MAISI Model 2, and Nvidia NIM demo. The limitation is it's currently the model is only supporting CT images and some out-of-box tumor tasks like the pancreas tumor still has gap with task-specific models because it's really hard to balance between this 25 data sets and also the 3D zero shot. Although it's improved by using those super voxels, but it's still not, it's distilled from the SAM checkpoint. So the 3D zero shot is not as impressive as the 2D SAM. This is something we need to improve. So the ongoing research, we're trying to support more modalities. This is straightforward to add MR into the same pipeline. Also, we want to achieve a better zero shot, 3D zero shot ability by distilling the SAM, SAM2, or use their data sets. That's it. Any questions?
Yeah, thank you, Yufan, for the excellent presentation. So the audience has some question for you. So the first is the OHIF plugin available now, or if it's available, where they can find it?
Yeah, I think it's under development. I mean, they will be released soon. So, but it's not available right now.
Okay.
Also, we have a local NIM demo. This will be locally available. Then if you can try this we have a research that this is the research repo, so you can try this on your local desktop, and it also provides a local user interface.
Yeah, that sounds good. So the second question is, do you think which components of Vista contribute most for the good performance compared to MetaSam?
Yeah, I think they're basically two different things. MetaSam is trying to use this fine-tune the SAM architecture on medical images. But based on our experiments, we also fine-tune the SAM2 on total SAM data. We found this, I think if you treat the 3D images slice by slice, it's not the optimal way, right? Because 3D, the leading 3D solution is usually based on 3D patch plus sliding window inference. When your models imported a 3D view, it's going to extract more information than those 2D slice by slice. And our experience showed that if we fine tune SAM2 on it's doing okay for good for like easy objects like the liver, spleen, or some femur bones, those with clear boundaries and like they are a single object. But it's doing really bad in those complex structures like vessels, pancreas, or columns that your 2D models will not work well.
Mm.
So
Yeah.
yeah.
Yeah, thank you. So the next question is how to compare models' performance depending on the choice of points. Some points may be more helpful for different models, right? For example, there may exist a set of points that maximize the performance of one model, but may deteriorate the others. How do you think about that?
What was the question?
So,
Selecting, yeah.
so how to compare the model's performance depending on the choice of points? The question is.
Yeah, there's no very easy comparison because usually people just do random selection. Yeah.
Okay. And the next question is, so do you guys have plan to release the curated data set?
Yeah, this data set is all publicly available, and I don't
So,
think we have the license to redistribute this data set, but we provide the JSON list. So every data set, including all the benchmarks, we provide the JSON split. So we have
so that
all
means, yeah, I guess his question is, do you guys have like curated some of the data sets? I guess that's it.
curated. Yeah, we gather them, then we for partial labels, they're already there, right? We don't do anything.
Right.
And for pseudo labels, we told segmentators to segment them. For super voxels, they're way too big, so we're not releasing that. We provide the code to generate this. You can generate everything in, yeah.
Okay. And the next one is for the dual branch design. Why do you perform prompts in full resolution? What do you think about prompting from the latent space?
Prompting in latent space. This is actually the latent space. This is feature. The only thing is, instead of using features here, we upsample it to a higher resolution. And you, people want to say if you want to use the prompting right here, but after that you still need to do the upsample. And here, remember this, we have the skip connection. So if you start doing prompting here, it's going to increase your training memory by a lot because you have those long skip connections to propagate the details. And here, if you at the end, you see this is just a linear projection. Also here is also linear projection with some cross attentions. So it's much faster. You don't need to recalculate this.
Right. Okay. So the next one is, so what batch size do you use for training? And do you use some unique normalization for different data sets?
Yeah, for data batch size, it's always a one patch and 128 cubic patch, and the prompt itself, because you see this image can contain like 120 100 classes, so the batch dimension is actually used by the class, right? So the batch dimension is actually the number of prompts. So we don't have like in each GPU we have multiple patches. Actually, for each GPU we only have one patch and lots of prompts. And also, if you want to say a lot, it's we're using multi-GPU training, so every GPU has a single image patch. So that's the patch size probably is we use 64 GPUs, sometimes 8 GPUs. So it depends on the number of GPU you're using. For normalization, it's remember the whole pipeline is built on a well-established pipeline using the instance normal or batch normal. We use instance normal here and the sliding window inference.
Okay, so due to the time limit, I'll read the last question to you. So can the model be fine-tuned on the CTA image, especially for the auto segmentation?
Yeah, it can be fine-tuned because this is just a pre-trained checkpoint. You can fine-tune it on anything you want. Yeah.
All right. Yeah, I think we thank Yufan again for the excellent presentation. So thank you, Yufan. So let's move to the next speaker. So next speaker is Tan. So her talk is medical AI for synthetic imaging. So Dr. Tan is an applied research scientist at Nvidia. Her research interests include medical image synthesis and foundation models. She obtained her PhD from Johns Hopkins University. She organized multiple MICCAI workshops and was the session chair of MICCAI 2024. So let's give time to Tan for her presentation.
Thank you, Dakai, for the introduction. Yeah, today my topic will be MAISI, medical AI for synthetic imaging. I will first introduce the contributors, then the motivation, and then the model, methods, evaluation, and the summary. MAISI was mainly developed by our brilliant colleagues Pengfei Dong and also me under the guidance of Da Guangxu. It received tremendous help from other Nvidia colleagues and our collaborators from NIH, University of Oxford, and University of Arkansas. The reason why we wanted to develop MAISI is because we noticed that there is an issue of lack of annotated data in the MICCAI community. There is limited data. Actually, for the data number is large. There's a lot of public data, but there is limited data with high quality annotations in medical imaging domain, especially those with tumors. That is because the expert domain knowledge is needed during the annotation, and also there is a long tail problem for deep learning models like rare disease. There are also privacy and ethical concerns on sharing medical data. That is why image synthesis is desired. There is another issue in this community, which is the lack of GPU resource. Especially when we are talking about image synthesis, the SOTA methods are diffusion models. Diffusion models require a large amount of GPU resource to train. Thus, we are developing foundation models that the users can use the foundation models to save GPU hours. Before developing MAISI, we explored the existing medical image synthesis methods. We found that there is some flexibility issue, that those existing methods often work just for a single dataset or only a few datasets. And they often work for a limited body region or limited organs or tumors. And often they work for specific voxel size or volume size. And they cannot generate large 3D volumes like larger than 512 cubics. That is why we developed the MAISI medical AI for synthetic imaging to address these issues. MAISI can be used to synthesize 3D paired image and mask. So taking this as the example, it can generate a paired mask like the left-hand side image, and the right-hand side image is a 3D CT images on the 3D different views. There are a few advantages of MAISI. The first is that MAISI can be used to generate a larger volume size range from small volumes like 128 cubic to large volume like 512 by 512 by 768 cubic, which is, as far as we know, the first attempt in realistic CT image dimension. It can also work for various voxel spacing, or some people call it voxel size. It can cover the whole body, and it can provide paired image and mask outputs. And for the mask, it can provide up to 127 anatomical classes, including regular organs and tumors. With these advantages, MAISI can be used for data augmentation, which can be used to improve segmentation accuracy with synthetic paired image mask. And we can also use it as a foundation model. Users can use it to save GPU hours, training GPU hours. MAISI is a latent diffusion model. It can consist of 3 parts. The first one is a foundation VAE, variational autoencoder. It is used to compress the latent features in order to save GPU memory for the next diffusion model. It works for both CT and MRI, and it works for flexible volume size and flexible voxel size. We also included the tensor parallel inside the VAE model to save GPU memory. The second part is foundation diffusion model. It can be used to generate large CT volumes up to 512 by 512 by 768 cubic. And it can be used to work for flexible volume size and flexible voxel size. And finally, the third part is control net that can adapt to different tasks. For the released control net, it can be used to generate image and mask pairs that can improve the downstream tasks, and it works for controllable organ or tumor size. We want to mention that the MAISI has a really nice expandability. If the users want to apply it to different tasks, we can just reuse the foundation VAE and the foundation diffusion model while only retraining the control net. That saves a lot of GPU hours. Many people would ask whether MAISI will require large GPU to train. Do everyone need a 80 gigabytes GPU to train MAISI? That's not necessary. The GPU requirement depends on the size of the image. For example, if you are dealing with a relative small size like 512 by 512 by 128, which is quite common for CT image, the minimum GPU memory requirement for training and inference is just 16 gigabytes. And for image size, like large image of 512 cubic, the minimum GPU memory for training is 40 gigabytes, while for inference is 24 gigabytes. Below is the peak GPU memory for the diffusion model and the control net training. We can see that, as we mentioned, for the 512 cubic, the peak memory is just is smaller than 40 gigabytes. And if you are dealing with the ultra large image like 512 by 512 by 768, the peak memory is less than 80 gigabytes. And if you are dealing with relatively small size image, like 256 cubic, the peak memory is even less. So how the MAISI inference API look like? The users, to get a paired image like this, users would need to give us the voxel size, the voxel spacing. For example, the users wanted 512 by 512 by 768 cubic, and the users wanted 1 by 1 by 1 by 0.8 millimeter. And the next input is the body region. For example, whether users want a head or chest abdomen or lower body. And also the interesting anatomies. For example, a liver or kidney or lung, a list of anatomies. Then with this input, the MAISI will provide output which are a paired image and the label mask. The labels are corresponds to those anatomy lists that users provide. Here is an example of how it looks like for our GUI demo. I put the link here. The user will so in this example, the user asked for a body region of abdomen. And a list of anatomies including liver, spleen, left kidney, and right kidney, and ask for a size of 256 cubic and the spacing of 1.5 millimeter. And by click this run, we will get a result on the right hand side, which is the image and the mask overlaying on it. How about the algorithm of MAISI? The training consists of 3 parts. The first part is a VAE GAN. So it takes 3D medical images and compresses it to 3D image features. There are a few losses: L1 loss, the LP-IPS loss, which is a perceptual loss, the KL loss to regularize the latent space, and finally the voxel loss to make sure that the image looks realistic. So all the models in our MAISI are 3D deep learning networks. The second step is the diffusion model, which is a latent diffusion model. With the schedule noise, it predicts the noise. It's a pretty standard diffusion model. But in addition to a vanilla diffusion model, we added the body region and the voxel spacing as its condition. The third part is a control net. In addition to the body region and the voxel spacing, we also added the segmentation mask in the control net training. For the users with different applications, we can change the input and change the input condition to work for other applications. So these are the data we used during the MAISI training. For VAE, we used the 39K CT data covering whole body and 18K MRI data covering brain, skull stripped brain, chest, and abdomen. We randomly zoomed the original image to support variable voxel size. And second part is foundation diffusion model. We trained with 10K CT subjects from 24 datasets covering whole body, and the data distribution is shown in the figure below. We can see it covers a large range of the data volume, size, and its voxel spacing. And the final last part is the control net. It can be used to adapt to different tasks. We trained 2 control nets, sharing exactly the same foundation VAE and foundation diffusion model. The first control net, we call it MAISI CTGen. It takes mask as input, generates paired images. We use the 6K CT images and their auto-segmented mask as training data. The mask have 127 classes. The second control net is MAISI InPaint. We take the image and the tumor mask as input, and we inpaint the tumor on the input image. We use only 380 medical MSD images and their tumor mask as the training data. Now we can see that the control net can be trained with a really small number of training data. And this is the inference algorithm. We first use this control net diffusion model to generate the 3D image features and then decode the image features with the VAE. I've talked a lot about the advantage of MAISI. So how's the number looks like? So next we'll introduce the performance evaluation. We did performance evaluation for each of the three parts. The first one is foundation VAE. The goal is to test whether this foundation VAE is really foundational. We want to test whether it can zero transfer to unseen datasets. We tested on 3 datasets, MSD7 and MSD8 and BRAS 18. None of them has been seen during the training of VAE. We tested on field matrix, SSIM, and PSNR image similarity, and LPIPS is the perceptual loss. We compare two things. One is MAISI VAE, which is we directly apply the MAISI VAE to auto-distribution datasets. So it's unseen, we've never seen it before. The second one is dedicated VAE, which means we train a new in-distribution VAE on those datasets, on those 3 datasets. So we are comparing out-of-distribution VAE to in-distribution VAE. And here are the results. And we can see that for MSD7, which is the CT dataset, the MAISI VAE is actually slightly better. And for MSD task 8, which is also a CT dataset, the dedicated VAE is slightly better. And for BRAS 18, which is an MRI dataset, the MAISI VAE is slightly better. So we can see that the MAISI VAE is at least can achieve comparable results with the in-distribution VAE. And the good thing about it is the GPU hours. When we apply MAISI VAE, which means there's no training GPU hours, we just directly apply it. For the users in the real-world application, we can directly apply it or just fine-tune it for a really small time period. That would work. Comparing to training from scratch, that will take a large amount of GPU hours. And the second part I'm comparing is foundation diffusion model. Here's the example, is a qualitative example comparing to other methods. The first one is DDPM, which means there's no VAE here, just comparing the diffusion model. It takes a huge amount of GPU memory. That's why we can only do it for small volume size. That's why it's smoothing. And the second is a vanilla latent diffusion model without any modification, just vanilla latent diffusion model. And third one is the GAN method. And finally, the MAISI, we apply several modifications to the vanilla latent diffusion models, and we get the result that's visually much better than the other comparison methods. And on the right-hand side, we are showing that MAISI works for various volume size and voxel spacing. So we have different volume size and different voxel spacing on those 3 images. We can see that MAISI generalize well. And here are the numbers for the foundation diffusion model. The goal is to test whether the synthesized images look like real CT images. So we are comparing with FID, which is a metric measuring the distance between feature representations of real and generated images. In short, it tests whether generated images look like real CT images. So what we are comparing? We are comparing MAISI results to first we are comparing MAISI results to in-distribution real CT images, which means that these 3 datasets we already seen during training. And we want to mention that we first want to compare real to real, which means we are comparing, for example, LIDC to MSD task 6 for both are real images. We want to know what's the upper bound, what's the lower bound of this FID. And we can see that even for real to real, the FID is around 3 or 4 or 1.8, just around this range. And next, we are comparing synthetic to real. We can see that for the GAN method, the FID is too large. And for MAISI, we can achieve a FID around 4 or 7 or 6 or 8, while the real images are 3 or 4. So the MAISI synthetic image already achieved a really nice FID score. Next, we want to compare whether the MAISI diffusion model works for auto-distribution real CT image, because we claim it to be foundation. So when we are claiming something to be foundation model, we want to see how it works on auto-distribution model, auto-distribution images. And here are the results. We compare several different methods, and the MAISI diffusion model achieved the best FID score, and we compare FID on the 3 different views, and average is around 6. So we are comparing to a AutoPet dataset we have never seen it during MAISI training. And FID score is around 6, which is, of course, not as good as real-to-real, but pretty close already. And the last part we are testing is the control net. We want to test whether this control net can improve the performance of segmentation. We say that, okay, the control net, the MAISI control net provide a lot of paired image and mask. If we use those paired image and mask, can we improve the segmentation dice? We mentioned that we trained 2 control nets sharing exactly the same VAE and the diffusion model. One is the MAISI CT gen, it generates image and mask pairs. Another is MAISI InPaint. It InPaint tumors on healthy input CT images. And for the segmentation algorithm, we use the Auto 3D Seg, which is a automatic segmentation pipeline, and we train each model from scratch. Train each segmentation model from scratch. We conducted 2 sets of experiments. One is real, which means we train a segmentation model using only real data. The next is real plus synthetic, which means that we mix the real image and the synthetic image for segmentation training to show the effect of synthetic data for segmentation data augmentation. And we can see that the MAISI CTJ, the MAISI CTJ, MAISI InPaint almost always improve the segmentation results compared with the real only. We also compare with a comparison method which is called difftumor. So we can see that the MAISI InPaint achieves at least comparable results with difftumor, and both MAISI CTG and MAISI InPaint helps as a data segmentation method for segmentation. So for writing a paper, that's enough, but we want to know whether MAISI can be used as a real application, whether it works for a real-world scenario. As Yufan just mentioned in the previous talk, they developed the Vista 3D, which is a foundation segmentation model. And during the Vista 3D training, we met the issue that there's lack of annotated tumor training data. We used the MAISI CT gen to increase the number of tumor training data for Vista 3D by 100%, which is the real plus synthetic data. When we say increase the data by 100%, it means that when there are, for example, if there are 100 real image, we synthesize also 100 images to add to the training data. The result is shown in the table. For the Vista 3D, for the last year's RSNA release, the tumor segmentation average is this 47.3 as a dice. And after we fine-tuning the tumor, it increased a little bit, but not much. But then we added the MAISI synthetic data during the fine-tuning, and the result is improved significantly. And the nice thing is that it improved the tumor segmentation result while not affecting the segmentation performance of other anatomy structures. So that is what we desire. In summary, MAISI is the 3D medical image latent diffusion model, which consists of 3 parts: foundation VAE, foundation diffusion model, and a control net that can adapt to different tasks. It can be used for data augmentation. It improves segmentation accuracy with synthetic paired image mask. And the released control net can output image mask pairs used for data augmentation in our segmentation foundation model with the 3D. And the foundation VAE and foundation diffusion models can be used to save training GPU hours for the users. And in the future, we are planning on a few works. For example, we plan to support more modalities such as MRI, and we want to accelerate the inference speed for MAISI, and we are planning for more applications than segmentation. MAISI paper, we have a paper and it's already accepted at WACV 2025. Finally, thank you. Time for questions. We have the paper and a GitHub repo, which contains all the code and the model ways, and there's a GUI demo as we shown before. Thank you.
Thank you, Chen, for the excellent talk. Yeah, we got a couple questions for you. So the first is, are the MAISI code and model weights publicly available right now? I think so,
Yes.
right?
Yes, it is.
Yeah. And the next is, what's the computational time to generate one typical size and one large size CT volume?
The inference time. Yes, so
I
inference
think so.
time is currently for a small size like 200 and oh, let me share the we have a table. Mm. Yeah, can we see the table?
Mhm. Yes.
Yes. We put the time cost and GPU memory usage in our GitHub repo. And for a small size like 256, the diffusion model takes 81 seconds and the VAE takes 7 seconds. And for a really large volume, for example, like 12 cubic, the diffusion model takes a longer time, like over 500 seconds, and the VAE is 29 seconds.
Mhm.
And the GPU memory is small.
Mhm. All right. Yeah.
Yeah, and that's what we are planning to improve. We want to have a acceleration algorithm. That's what we are developing.
Mhm. All right. Sounds good. So the next one is how to make sure the control net training with less number of images does not lead to overfitting. Will that be a problem for the model?
Um, so that's a really big question. How to train your model to avoid overfitting? I would say that you follow the general rules, like how you avoid overfitting. You apply the documentation or you control the time to stop the model training. It's just how you avoid overfitting in a regular model training.
Right, because in your case, the data is not small. Yeah, so right.
Yeah, it depends on your data sets. Yeah.
Right. So then the next question is, did you observe some patch inconsistency for the VAE training? And if so, how do you solve them or handle them?
So what consistency? Could you
Uh,
help repeat again?
did you observe some patch inconsistency for the VAE training?
For the VAE training, I guess the question is about the stitching artifacts during the inference, because in the VAE training we just randomly crop patches for
Mhm.
VAE
Yeah,
training.
right. When you combine them to the inference, are there some patch inconsistency?
Yes,
Because
we noticed it if because during the VAE decoding, we use sliding window to reduce GPU memory. Of course, if you have really large GPU, you don't need sliding window. But if you have a small GPU and you have to use sliding window, there might be some stitching artifacts, and we can control it by this parameter of the sliding window overlap. If you increase the overlap, the stitching artifact will be eliminated. Yeah,
Mhm.
but that will increase your inference time, so it's a trade-off.
Mhm. Okay. So the next one is, how did you compute the FID on 3D images? Are they using 2D slices?
Yes, we are actually computing 2D FID on all the three views.
Okay.
Yeah, I think I should have numbers here. Yes. So
Mhm.
we are comparing the XY plane, YZ plane, and ZX plane.
Okay. So the next question is, so LIDMs are around for a while. So where does the huge memory reduction come from in the MAISI model?
Yeah. So the first of all, we have the VAE gun, that will compress the images by memory to 4 by 4 by 4 by 4 as the downscale. So if your image is 512 cubic, the latent space will be 128 cubic. I should have it here. Yeah. So
Mm.
that's the compression. So it's 16 times compression. That saves a lot of GPU memory for diffusion model.
Okay. And the next one is, did you use any type of pre-trained weights for the diffusion model and the control net?
No, we haven't. We trained our diffusion model from scratch. And the control net was trained from diffusion model weights, just as a regular control net would do.
Okay. And the next question is, so for the segmentation mask, you just use the augmentation, right?
For the segmentation mask, the input here during the inference, yes, we use some augmented segmentation mask. But for the users, you can use your own segmentation mask.
Okay. And the next question is, did you evaluate the generated images with the radiologist and asking them, how they feel the realistic is?
That's a really good question. That's something we are doing.
Okay, sounds good. And did you observe some model collapse when training with synthetic data?
We did not really. So the segmentation training for us is quite smooth.
Okay. And I guess because of the time limit, the final question. So, have you used your generated city image to test for downstream task, like segmentation of the lung? Yeah, I think so. You used
Yes,
and
yes,
in
we used, yeah.
right
I
and
didn't put it here, yes, but we did some, we have some dice result.
right.
Yeah.
And using the synthetic city image, does it reduce the segmentation model inference? I don't think so. That will just affect the
Yeah,
performance.
it just affects the training, the performance. It won't affect the inference time.
Okay. Oh yeah, I think that's a good question. The final one, really final one. So did you work with the original Huntsville unit intensity or use some other normalization?
Uh, yes, we did not work with Huntsville unit during training, but we have a quality control. That for the generated image, we test whether its Huntsville unit is, for the major organs are within a correct range. If it is, we say its quality passed the check.
Okay, so basically you don't do the normalization on the city image, right?
No, we just clip the minus 1,000 to 1,000. Just
Okay.
the clip, yeah.
Okay, that sounds great. Yeah, I guess the time is here, so we thank Tan again for the great presentation, and we'll release the recording shortly in the future. So thank you, thanks the audience again for participating in this MICCAI Industry Talk. I hope you all enjoy it and yeah, learn a lot. So we thank Yufan and Tan again, and see you next time.
Yeah, thank you, Dakai. And for if you want to ask any questions, welcome to raise question in our GitHub repo. And also, if you want any features, for example, you want MAISI or Vista for MRI, you want MAISI or Vista for PET image, you just raise your feedback in our GitHub discussion.
Okay.
Yeah, thank you.
Yeah, thank you. Bye bye.
Bye.